Hello everyone, thank you for all organizers of this conference. My name is Khaled Al-Maitah, and the title of our study is Artificial Electric Field Algorithm for Optimum PMU Placement. And my co-authors are Professor Khalid Moore and Engineer Batul Khlisat. Firstly, introduction about the wide area measurement system, where nowadays the power system becomes more complex and it's monitored by a SCADA system. Actually, conventional SCADA systems are limited to steady state measurement and cannot be used for observing the system dynamics. But the wide area measurement system or wide area monitoring system enables the power system dynamics behavior to be permanently monitored. Actually, wide area monitoring system is one of the most important technology in the modern power system, and it is considered as one of the primary systems to develop the existence power grid to be smart grid. Wide area measurement system capable to provide real-time view of dynamic behavior of the electrical variable. It gathers synchronized time-step measurement from wide area across the power system. To do that, we need a high reporting measuring device such as phasor measurement unit (PMU), where PMU able to gather synchronized measurement and set it to the phasor data concentrator through communication system, where the phasor data concentrator PDC able to gather the synchronized measurement from single PMU or from multiple PMUs. Practically, PMU are installed in the substation and they are connected with CT and VT. That means when a PMU has been installed at any bus, it can measure the phase voltage of that bus and the phasor current of all branches that is connected to that bus. Actually, due to the high cost of PMU itself and its installation cost, it's not practical to install PMU at each bus in the power system. From this point, many researchers have taken the question of optimum PMU placement or optimum PMU location to select the optimum number of PMU and their location for full observability of the power system. The main objective of optimum PMU placement problem is determining the minimum number of PMUs to provide full observability of the power system. There are two main scopes of the problem. The first one deals with problem formulation, and the second one deals with optimization techniques that have been used to solve the OPP problems. Actually, there are two main contributions of this study. The first one is the comprehensive cost model, where a realistic cost model of OPP problem has been proposed in this study. The proposed includes the PMU cost, PDC cost, and additional cost, where the additional cost of the proposed model represents the needed to upgrade the some devices such as voltage transformer, current transformer, and communication devices that will be used to upgrade the communication infrastructure of the substation. And the second one is by using the artificial electric field algorithm, which is a novel optimization technique was proposed in 2019, where based on the author knowledge, this optimization technique did not use yet to solve any type of OP problems in the literature. In general, the OPP problem is formulated as an optimization problem, where it has an objective function and set of constraints. The objective function aims to minimize the number of PMU as a following, where n represents the total number of passes of the system, and x is represent the PMU location, where each pass in the power system has its corresponding value or corresponding x variable, and it's equal 1 if there is PMU installed at this bus, and otherwise it will be 0. However, this objective function is subjected to the following constraint, which is called as observability constraint, where A is the connectivity matrix of the entry system. In the proposed cost model, the total installation cost of wide area monitoring system is considered as an objective function to determine the optimal number and location of PMUs in the power system. Thus, the objective function was given as a following to minimize the total installation cost of WAMS, which includes the PMU cost, PDC cost, and upgrading cost, where the upgrading cost was calculated by the cost factor multiplied with a number of branches in the substation. Additionally, this objective function is subjected to the observability constraint as previously stated. To solve this optimization problem, the artificial electric field algorithm is used in this study actually. As any heuristic optimization algorithm which are inspired from natural phenomenon, the artificial electric field algorithm inspired from electrostatic force between charged particles, where in this algorithm the charged particles are the agents in the algorithm and the charge value is the strength, where the electrostatic force controls the motion of these charges or agents in the search space, and the final position of these charges is the solution of the proposed problem. In this study, 5 IEEE test systems are used to demonstrate the ability of artificial electric field algorithm to solve the OPP problem for small and large power systems. However, the test system includes the IEEE 14 bus, IEEE 13 bus, 39 bus, 57 bus, and 118 test system. The first result was obtained by using the artificial electric field to solve the general formulation of OPP problem, where this table represents the number of PMUs and their location for all test systems. The study was done by considering the zero induction bus and without, where the zero induction bus refers to the bus that does not have any load or generators. For example, in IEEE 13 bus test system, we need 10 PMU to achieve full observability, and this is their location. This is for without considering the zero injection bus. If the zero injection bus is considered, the number of PMU can be decreased to 7 PMU, and this is their locations. As a comparison between the artificial electric field algorithm and other optimization techniques, this table presents this simple comparison between the artificial electric field algorithm and integer linear programming techniques, genetic algorithm, and particle swarm optimization. It's observed all these algorithms can provide us same result actually for number of PMUs in the test systems. For more elastic, for the proposed cost model, the cost of PMU and other related equipment were taken from United States Department of Energy's Office of Electricity Delivery and Energy Reliability. This table represents this cost, where the PMU cost is considered as $14,000 and PDC cost is considered as $8,000, and the additional cost is are considered as $12,000 per branch in the substation. By using the proposed model, the optimal number of PMUs and their locations that provide the minimum cost of wide area measurement system for each test system was obtained using a artificial electric field algorithm, and it are presented in this simple table. For example, to implement a wide area measurement system in IEEE 13 bus test system, we need actually 10 PMUs, and this is their location, and the minimum cost will be about $876,000. This figure presents a comparison between the general OPP formulation that based on minimize the number of PMUs with the proposed cost model that based on minimize the total cost of installation or total installation cost of wide area measurement system. It observed the proposed cost model enhances in decreasing the total cost of wide area measurement system implementation. For example, the proposed cost model decreased the total cost by 50% in IEEE 14 bus system, and so on for all test systems. As a conclusion of this study, a cost model was proposed to solve the optimum PMU placement problem. It represents a realistic cost model of wide area measurement system implementation. The proposed model was solved using artificial electric field algorithm, and the result of this algorithm was compared using other related optimization techniques. As a result, the proposed model actually provides the designers an overview about the wide area measurement system cost with depending on the required reliability of the power system. And finally, thank you for your time, for your watching, and I hope to see you in the next conferences.